We're going to do some examples for linear independence. Our first example is to determine whether these two vectors are linearly independent. This is actually a really easy example. 0 should not be in any list of linearly independent vectors. So automatically, these vectors are not linearly independent. We're only left with 1. So now this one vector is a linearly independent set. So now that goes out of the way. Next example gives us these two vectors, and we're asked to find if they're linearly independent. So 2, 1, and 6, 3. So to check if these are linearly independent, we got to check if there are any coefficients. So we'll call them C1 and C2, such that C1 times our first vector plus C2 times our second vector will equal the 0 vector. So this ends up just being a system of equations. Maybe I should write this like this. And we can just write this in its augmented form. And when we row reduce this, we can swap the first and second row, and then subtract. Subtract the first second row by 2 of the first. And since we can't get the identity matrix, one of our vectors is not linearly, these two vectors are not linearly independent because we can, this is pretty much saying C1 plus 3C2 equals 0. So we can choose any combination of C1 and C2 for which this is true. So if we have C1 equals 1, then C2 would equal negative 1/3. So, whoops. The bottom line is, if we can find constants like this that are not 0, that means the vectors are not linearly independent. So now if we look at our reduced row echelon form, we see that we have a 1 here and a 3 here. And what this tells us is that the second vector we had, 6, 3, is 3 times, is a multiple of the first vector. More specifically, it's 3 times the first vector. So if we took this vector, we multiplied it by 3, we'd get our second vector. So if vectors are multiples of each other, then they're not linearly independent. So we can throw that one out, and now we're left with one linearly independent vector. Okay, so we have one more example. We have these 3 vectors, 1, 0, 0, and 1, 2, 0, and 1, 2, 3. So to check if these are linearly independent, again, we want to find constants. So non-zero constants for which their sum will equal the 0 vector. If we can't find those non-zero constants, then we have a linearly independent set. So we can put this in we can put this in matrix form. And we can row reduce, so multiply our 2 by 1/2. Then we can subtract R2 from R1. Then we can multiply R3 by 1/3. And finally we can subtract R3 from R2. So now this is telling us that C1, C2, and C3 all equal 0. So since we can't find non-zero constants for which some of these vectors will equal the 0 vector, these are all linearly independent.